All right, welcome. So for this lesson here, this is section 3.4 in your textbook Pre-Calculus 30. We're going to be talking about equations of graphs of polynomial functions. Now we've already looked at a lot of aspects of the graph, like end behavior, right? And we know about intercepts. We know about x-intercepts. We know that the constant in a polynomial function is the y-intercept. So we've pieced a few things together already. We're going to talk about a couple more important, well, not more important, but a couple other important things today. And the first one is going to involve the roots or the zeros of the equation. So we're going to talk about roots and zeros and what they are and what they look like on the graph, where they are on the graph. We're also going to talk about where a function, so that would be like the whole function itself, y equals that whole graph, the whole function. When is it positive and when is it negative? We'll be able to look at a graph and be able to see that and identify the x values that cause a function to be positive or the x values or the domain that cause the function to be negative. So we're going to talk a little bit about that. We're going to introduce this word, probably really new to you, called multiplicity. What is that and what does it mean? And by the end of this lesson, we're going to be able to piece together a lot of information about the graph of a function without actually graphing it. And so that's a huge part of, that's a big part of calculus actually. Like when you get to calculus, there's a whole section about curve sketching, and we use a lot of this stuff as the basis point for sketching very complicated curves. We also do calculus applications as well, finding derivatives, finding local extrema, and all that exciting stuff. But this is sort of the base, so you'll learn this first. All right, so this was the this little activity from your textbook. You'll see this in your textbook, page 136, if you're following along in McGraw-Hill Ryerson Pre-Calculus 12. And I've asked you to graph this function right here on your graphing calculator. So this is the first step right here. Okay? Do you have a graphing calculator, everyone now? Does everyone have one now? Okay. Hopefully you've had a chance to punch this into your graphing calculator. I am going to use Desmos, and this is the program that I'm choosing to use because it's going to help me greatly in showing you some other things. So this right here, correct me if I'm wrong, did I punch this in right? This should be the graph you're looking at. You may have to adjust your window, right? Because this does reach up pretty high. What's the y-intercept just offhand here? It looks like it's, yeah, it looks like it's 24. How do we know that for sure? Because of this constant right here. Very good. Whichever term does not have an x attached to it, okay, is the constant. And that constant is the y-intercept. Now, why would that be? Let's just go over that real quick. If I plugged 0 in for x, because this is where x equals 0. So if I plug 0 in for x, this term becomes 0. So this term becomes 0. This term becomes 0. And this term becomes 0. So all you have left is the constant. So the value of the function when x equals 0 is always the constant. Okay, very good. All right, so the question says, from the graph here, what are the x-intercepts of the graph? So let's look at this together, and I know you have that on your calculator, but let's just zoom in a little bit here. What are the x-intercepts here? They appear to be x equals negative 3, right? They appear to be x equals negative 2. And is this an intercept, do you think? Yes? Okay, most of you are saying yes. If we zoomed in a lot, okay, it looks like, yes, it is touching the graph at x equals 2, right? It's kind of funny. It looks like it comes right down here, and it almost touches the graph, and it's like maybe it's touching here, maybe not. But it for sure is touching right here at x equals 2. And if we were to zoom in even more, you would see, look at how close we're getting to 2 there. See, there's still some separation at 1.998. We can obviously see that. So the thickness of the graph here is obviously making it look like it's touching, but technically it is only touching at x equals 2 there. Okay, does everyone see that? So that's why I like to zoom in here with Desmos. It's awesome. Okay, so I zoom back out now. Hopefully we'll see this graph emerge. Okay, there's the full graph emerging again. Okay, awesome. So there does appear to be intercepts. We go back to our question at those 3 spots. Okay, very good. Now, what we're going to do is we're going to factor this polynomial, And we did this in the previous lesson, so if you need help remembering to factor, you might have to go back and watch that other video that we did on factoring polynomials. That would be section 3.3, PC 33.3. But we're going to take a moment just to do that here. We're going to factor this long polynomial fully into its factors. Okay? The job of factoring this polynomial here. And we've discovered that the factors look like this. The function can be written also as x minus 2 all squared times x plus 2 times x plus 3. So that's factored. What we then did is this is our original, okay? And we put our factors there. We put the same function in factored form to check to see if we did this right. And as I click off that one, see there's our original function, and now there's the factored form, and it is exactly the same. So we've factored that correctly. Okay. If you have the time on a test or an assignment or when you're working on your stuff, if you have the time, you can double check like this. You factored it just to check to see if you factored it correctly. Okay. All right, so if we go back to our questions here, how are the roots and the zeros related? You may not, you may be familiar with both of those terms, but the roots of the function and the zeros of the function are actually the same. Okay, they're the same. The roots of a graph would kind of be the x-intercepts. The zeros would be where, y equals 0. Okay, the solutions like this, if you let this equal 0, and this is sort of what number 2 says here, okay, if you let this equal to 0 and you solve, you would determine the roots of the equation. And so if you let this happen, right, what you would use is something called the zero product principle. You remember that, right? This whole product right here, the whole multiplication, is 0 when one of these factors, or all of them, are 0 themselves. So that is at x equals positive 2 for this one. It's also at x equals negative 2, right? Negative 2. And at x equals negative 3. Those are the solutions, right? So if you look back at that, okay, look back at the graph here, and I'll zoom back in, but we have roots of 2, negative 2, and negative 3. So 2, negative 2, and negative 3. That's exactly what we just said here. 2, negative 2, and negative 3. Okay? So the roots and the zeros of the function are the same, and they represent the x-intercepts of the graph. Okay? So that's very important. X-intercepts of the graph. So what do we notice? They are the same. All right. Let's talk quickly about when a function is positive and when it's negative. Okay? So it's a little trickier to tell from here when it's positive or negative, and I'm not going to get into sign analysis. Have you guys learned about sign analysis before in pre-calculus 20? We are going to be doing sign analysis again. I'm not going to focus on it right now. But if you have the factored form here, you can perform sign analysis, which many of you remember, to find out where the value of the function is positive and where it's negative. But if we look at the graph, so we're going to focus on this, we can also tell from the graph. So the function, that is the y values, are positive, okay, on this part of the graph where my arrow is pointing, right? This part, also all the way over to here. So this part in the middle, that's where the graph is positive, and jumping over to here, from here over to the left, you see? So the x values, where the graph is positive, you would refer to the x values that make the graph positive. So this function is positive when x is less than or equal to negative 3, or just less than negative 3 but not including 0, where x is between negative 2 and 2, and where x is greater than 2. So that's where the graph is positive. It's negative only in this section right here. So in this little section. So f of x is less than 0 when x is between -3 and -2. Okay? You may have to listen to that again. I'm not sure, but that is something that you have learned in previous classes. Okay. So let's get back to the notes here. And what is multiplicity? Okay, we're going to talk about multiplicity here. All right? Multiplicity. Multiplicity refers to the behavior of the graph at a zero. So, whoops, that's the wrong one. Where is it? Let's see, where is multiplicity here in our textbook? Multiplicity of a zero. Okay. So over here, and that's going to be for you on page what? 138, thank you. Page 138. So, the multiplicity of a zero. And when you refer to multiplicity, you're always talking about multiplicity of a zero, or a root, or an x-intercept. Okay? And it really basically refers to the behavior of the graph at that root, okay, or at that intercept. And how you determine that is by looking at this, and I'll explain this a little bit more as we move through, but the number of times a zero of a polynomial function occurs, that is the multiplicity, and that dictates the behavior. And I'll explain that more in a second. And really what the multiplicity shows you, or helps you determine from the graph, is what the graph behaves like at the zero. Okay, and I'll explain that. So a multiplicity of 1 looks like this, where the graph simply crosses over the x-axis. It just simply passes right through. A multiplicity of 2 looks like this, and we actually have this going on in our graph, right? So that's a multiplicity of 2. And 3 is sort of a combination of the two, actually. It comes here, and it looks like it's going to bounce back, but it actually kind of appears to kind of go tangent to the axis and then crosses over. So that's just a quick overview of the multiplicities. I'm going to talk more about that in a second. But let's just reinforce that with the graph. So what I want to do is I want to take these off now, and I want to light this one up right here. Okay? So what I have here, and it's maybe a little tough to see, but I have 3 zeros represented here because there are 3 different factors. All right? This is what the graph would look like if, and I'm going to have to zoom in here, maybe change my settings a little bit. Let's make that 3, make that 4. Okay? So look at what's happening here. There appears to be a 0 at x equals what? What's the 0 attached to this factor? X equals 2, right there. Very good. There appears to be a 0, or an x-intercept, at x equals +1, and that's true. There should be a 0, and this is maybe a little trickier, but at x equals what? 3 over 2. Yeah, what you do is you let this factor equal 0 and solve for x. That's all you do. So really, you'd be adding 3, so that's 3, and you divide by 2. So positive 3 over 2. And that's this one right here. All right. Now, the way I've got this set up is I'm going to show you what this would look like if the multiplicities were different. So right now, what kind of function do we have right now? Like as far as linear, quadratic, cubic, quartic, quintic, what do we have? We have cubic, yes. How can we tell? Well, one of the things that would indicate that is that it starts down here, right, in this lower quadrant. And really, if we zoomed out far enough, you see it's in quadrant 3, and it crosses the x-axis to go up to quadrant 1. So that's at least an odd function, right? Now, if you look here, I've got the exponent a set to 1. I've got b set to 1, and I've got the c, which is behind there. I've got that set to 1 as well. So to quickly find from factored form, you would go x to the 1 times x to the 1 times 2x to the 1. If you multiply those together, you get a cubed term. That's how you know what the function is. Again, there's a lot in this lesson, so you may have to just take some time to ingest this. But what happens now if I change this a value from 1 to 2? Watch the graph. Okay? maybe tricky to see, but at positive 2, oh, that's why it's tricky to see. Thank you. There we go. At positive 2, that would have worked too, but it's just tougher to see. So at positive 2, look at it doesn't just simply cross anymore. Look, here's 1. See? And here's 2. Notice how this behavior of the graph at this 0 changed, but the other ones didn't. Look at 1 and 1.5 when I just changed that a value. Look at, see? Cross, a simple cross, and a simple cross. That's because this is 1 and the exponent over here is 1. When I change this to 2, look at that. It doesn't simply cross anymore. It kind of comes tangent to but does not cross. All right? Now, if I changed b, that's this one, what do you think is going to happen at positive 1? If I change this to 2, what do you think will happen? It should flip. Okay, it should flip. But what should the behavior at? Will it still cross? It'll just cross the other way. All right, let's see. Ooh. Look at the behavior at this 0. When I changed this b value here to 2, you see, it went. It did the same behavior. See, it just kind of bounces off there. And then 1.5, that's this one, is still just a multiplicity of 1. So it crosses. And then at 2, you see here, I still have a multiplicity of 2. Okay? Alright, so what about C? Okay, this one is just a simple cross because the exponent is 1, but if I change that to 2, again, really tough to see, but you see how it kind of comes down? Tangent 2 comes back up. Goes down. Tangent 2 right there comes back up. Tangent 2 comes back up. Okay? Now, it would have been nice to show a little bit more separation here, which I might be able to figure that out, but maybe not right now. Okay, so what I will do though is I will make these adjustments here on the y-axis. I'm going to make this really small. There we go. Good for me. Okay. So again, bring that back to 1. That multiplicity, you see, is just a simple cross. Bring this back to 1. A simple cross. So cross is there because the multiplicity or the exponent is 1. Cross is over here at the 2 because the exponent is 1. But at 1.5, the exponent is 2, so it does this. So what happens if we take the exponent to 3? What do you think is going to happen at 3? Let's check. Ooh, that kind of looks like a bit of a cubic function, doesn't it? So that's your third type of behavior at 0. At 1, it's a simple cross. At 2, it comes tangent to the line, touches it at the 1 point, but then doesn't cross, goes back up. And if it's 3, it comes tangent to, and it actually touches and does cross over. Okay? So watch this middle one here as I let this kind of play. So you see it kind of bounces from straight to kind of a parabola, now to cubic, now again more parabola, cubic. And what happens is when it's 1, it's a cross. When it's even, it's tangent to but doesn't cross. And when it's odd, it's tangent to and crosses. Okay? So that's 2. There's 3. There's 4. There's 5. You see? And of course, we could do that for the other ones as well. There's 2. There's 3. I'm looking at this 0 right now. There's 4. There's 5. And the other one, there's 2. Whoops, there's 2. There's 3. There's 4. There's 5. So we're looking at this 0, right? Okay, now let's play them all together and see what happens. Let's slow that down. Okay, so the multiplicity is, notice that the actual intercepts themselves aren't changing. So if we draw a chart here just to summarize what we've been talking about, a multiplicity of 1, okay, and that means that the factor itself, let's say it's x minus 2, just shows up once in the list of, and the multiplication of factors of a polynomial. So that's a multiplicity of 1. The behavior is the graph just crosses the x-axis at that intercept point, okay, it just crosses. And a sketch would look something like, if we just had this, the sketch would look, just something like this. It just straight crosses, like that. And it's a kind of a straight line immediately around the x, straight. Okay? If we had a multiplicity of 2, so like this factor up here, if it showed up twice in the list, multiplicity of 2, or really any even number, okay, so really any even number, it's tangent to, but does not cross. And that graph would look like this. Comes down like a parabola, just touches and goes back up. And finally, just one more here that we'll summarize today. A 3, or really any odd, okay, is this. Tangent to and crosses. And of course, that graph would look something like this. Okay, it kind of comes up, it sneaks up to the line. It actually does cross the line. All right? Okay. So that's kind of the big lesson on the zeros. We didn't answer that last question formally. We didn't answer that last question, but we'll just go over it real quickly here right now. What can we determine? Well, we already knew about intercepts, y, and now we know that the factors represent the zeros, which are the x-intercepts. You know end behavior, and now you know something called zero behavior. That's what the multiplicity dictates, the behavior at the zeros. So multiplicity is zero behavior. So if we just summarize multiplicity, it dictates the zero behavior. And that zero behavior would be a new term that you've heard. And so really what that is how the graph looks immediately next to the x-intercept. So these are just examples over here, but if it's a multiplicity of 1, it's a straight line immediately around the intercept there. Here it's like a parabola immediately around the intercept, either opening up or opening down. Could be either way. And of course here with its odd, it kind of looks like a cubic function as it crosses the x-intercept. So there's your summary of multiplicity, and that's the lesson on how the characteristics of an equation can tell you about what the graph is going to look like.